Thank you for the opportunity to present my paper in the 16th edition of International Conference on Electronics, Computers and Artificial Intelligence. The topic of the presentation is a unified ECG paper digitization framework with RPIC detection for RR interval analysis and deep ECG learning applications. Myself, Jomol Varghese Vadakan, and my co-authors are Dr. M. Shabramalai Manikandan and Dr. Lingareddy Sengaramati. This is the outline of my presentation. I'll start with the introduction, literature review, major objectives of the paper, proposed method, results and discussion, conclusion and references. Introduction. The cardiovascular diseases are the leading cause of death worldwide among the non-communicable diseases. Electrocardiogram signals are used as non-invasive diagnostic tool in most hospitals to analyze cardiac arrhythmias. The ECG signal represents the electrical activity of the heart that consists of local waves such as P wave, QRS complex and T wave. Experts visualize the wave amplitude, duration, interval and shape to detect the heart abnormalities. Classical ECG printouts are commonly used in primary health centers, ambulatory services and hospitals to print the data as a document or image. The ECG paper records are cost-effective without the additional expensive storage hardware and trained technician to handle the digitized records. Past studies have attempted to digitize the paper ECG tracings using telemetry system, but it is time-consuming due to the lack of digital records at hospitals. Expert service is required when the ECG signals are corrupted during printing and scanning. Visual inspection of paper-based ECG record is challenging and time-consuming for the large number of ECG records. The major objective of converting the paper ECG records into digital ECG record is we can preserve the different variety of cases, arrhythmia cases from the paper ECG, and we can preserve it for future studies, and we can utilize large volume of paper ECG signals available for deep learning based ECG analysis. Literature review. There are different variety of techniques used for the paper ECG digitization, starting from open source software to MATLAB related tools and machine learning methods, image processing techniques. So here we are implementing with image processing techniques. We propose a simple automatic ECG paper record digitization method that generates 1D ECG signal and detect RPICs, which can enable automated ECG signal analysis under low resource settings, and to evaluate the performance of the proposed framework using scanned ECG paper with different image qualities, different kinds of PQRST complexes and multi-lead signals. The block diagram represents the proposed method for a unified ECG record digitization framework. It consists of grayscale conversion, edge detection, horizontal profiling, ECG signal generation and RPIC detection. The first step is the color image to grayscale image conversion. The grayscale image conversion helps to implement the uniform ECG image representation before performing the ECG lead segmentation, and it helps to reduce the overall computational resources. Figure 1a represents the scanned or JPG image of the ECG image paper, and figure B represents the grayscale image conversion. The next step is edge detection based image binarization. So the edge detection can be done using different methods such as fixed and adaptive thresholding approaches, but here we are doing with a gradient based edge operators. So the binary image obtained by thresholding the gradient magnitudes, and here we are using the pivot operator. The pivot based edge detection results in better preservation of the ECG traces and removal of the grid lines. So the output of the edge detection based binarization is shown in the figure. The next step is the ECG lead segmentation, which involves horizontal profile creation, midpoint calculation, and lead image cropping. The horizontal profile creation helps to compute the number of leads in the scanned ECG image, and the midpoint calculation helps to segment the ECG image into single lead ECG images. So this is the figure which represents the horizontal profile creation. Here we have 3 leads of ECG images, and which is smoothed out and detected the midpoints. Then next step is the ECG signal generation from the segmented ECG lead image, which involves the steps such as binary image dilation, isoelectric line extraction, upper and lower half waveform extraction, ECG signal reconstruction, waveform smoothing. So the figure represents the cropped single lead ECG image, and the dilation operation with the line shaped structuring element is used to thicken the ECG trace lines in the segmented binary image, which fills the gaps between the binary images. The isoelectric line extraction is applied to preserve the polarity of the ECG signals, that is performed using the horizontal profiling of the dilated image. With reference to the isoelectric line portion, we extracted the upper and the lower half of the ECG traces, and we will reconstruct the original 1D ECG image, and in which we are detecting the R peaks using the R peak detection algorithms already existing. So moving to the results and discussion, here we are analyzing the MIT-BH evaluating the performance of the proposed method using MIT-BH arrhythmia database. It contains 48 records and 2 leads, and the table is formed with the help of detected R peaks for the 2 leads, and here we are taking the ground truth and digitized ECG images. Digitized ECG signals. So for lead 1 and lead 2, we are detecting the R peaks in both ground truth and digitized ECG signal, and it shows a better correlation between the both. The common metrics used for the evaluation of the result is Pearson correlation coefficient. So for lead 1 and lead 2, the results are shown in this table. So for more records, it is showing 100% correlation. If you look record number 100, for ground truth, it is detecting 13 R peaks, and for digital ECG signal, it is detecting 13. So the correlation is 100%. And if you consider the total correlation coefficients for lead 1 and lead 2, it is achieving around 0.93 and 0.94 for lead 1 and lead 2 respectively. The table shows the comparison with the existing methods, and here a fair comparison is difficult because they are implemented with the different types of databases. Even though we can analyze that we are obtaining a Pearson correlation coefficient near to the existing values, so we can tell that our method is getting better correlation coefficient ratios. So moving to the conclusion, we presented a fully automated ECG paper record digitization framework with R-peak detection. The performance is evaluated using different image qualities with multi-lead and different kinds of PQRST complexes. The method achieved a Pearson correlation coefficient value greater than 0.93 by detecting the R-peaks. The evaluation results demonstrated that the unified framework provides promising result in determining the number of leads in ECG scan, lead segmentation, and preserving the R peak. In future, the performance of the method will be evaluated using different kinds of ECG image distortions. These are my references.